All right, guys, we are on our last chapter. It is chapter 8, which deals with series. Okay, but the very first section, 8.1, deals with just what's called sequences. So today we're going to talk about sequences, and then in the next one we'll talk about the difference or the similarities and differences between sequences and series. Okay. All right, so today just sequences. What is a sequence? A sequence is a list of numbers written from a pattern. Okay, so let's take a look something like 1/2, 2/3, 3/4, 4/5. All right, and then dot, dot, dot. It keeps going on. All right, can you see a pattern here? Okay, and you want to relate it to, like, this is a sub 1. This is a sub 2, this is a sub 3, and this is a sub 4. Now, it's nice if you can relate it to the previous one, but it's even better if you can relate it to just its position. Because if I want the 70th term and I'm relating it to the previous one, then I got to go find 69. And if I have to find 69, then I have to find 68. But if I can relate it to the number 70, to its location, then I can just go right to 70 and say, okay, I know what 70 is. If I want the 100th term, if I can relate it to 100, then I can find 100 right away. If I'm relating it to the previous term, then I have to write all 100 terms out. So it's always better if we can relate it to this guy, and this guy is called n. So this problem, it would be n and then plus 1. N plus 1. So we would say a sub n, the pattern is n over n plus 1. Okay? Or eventually we're going to see it written like this. A sub n equals n over n plus 1. Okay? Now, not all of them have a pattern, and don't panic. Right, very little in this chapter are we going to have to come up with the pattern on our own. So we'll talk about that when we have to, but just understand that it's better to associate it with this n value. Okay, and that's how we're going to see it most of the time. This one we can relate to. Let's take a look. 2, 4, 6, 8, dot, dot, dot. This is a sub 1, this is a sub 2, this is a sub 3, and this is a sub 4. Okay, so how can we relate it? How do we go from 1 to 2? We know maybe we can do something like this, but it's much better to relate it like this. 2 and 1, or how do we go from 2 to 4? How do we go from 3 to 6? How do we go from 4 to 8? So that would be a sub n is 2n. Okay, remember it's okay to do it this way, much better to do it this way, and the whole reason why is now I can come up with the 100th term without having to go backwards. Okay, so we're going to see it as a sub n equals 2n. Okay. All right, not all of them have a pattern. I'm sorry, not all of them have a pattern that you can write out. This one has a pattern. Let's see if we can come up with this pattern. 0, 6, 0, 0, 6, 0, 0, 0, 6. All right, so this definitely has a pattern, but it's not really possible to write it out in terms of n. Okay, and that's okay too. Not always possible. This one we can actually. It's -1, 1, -1, 1, -1, 1. You get the idea, dot, dot, dot. This one we actually can. A sub, oops, so this would be a sub 1, a sub 2, a sub 3, a sub 4. Notice all the even ones is positive, right? And all the odd ones are negative. So we could write a sub n, and we could do -1 to the n. So if it's negative, or I'm sorry, if it's odd, it'll stay negative. And if it's even, it'll go positive. And that works perfectly. So we would write a sub n equals -1 to the n. Okay. Probably the most, let's see, can I sneak it on here? I'm just going to slide this up now. Okay. The Fibonacci numbers, you can relate those right? 1, 1. Okay, you have to start out with that. Then you add those two together, 2. Just add the next 2, that gives you 3. Add the last 2 numbers that you wrote, that's 5, right? Add these 2, that's 8. We get the idea. Add those 2, that's 13. We could add those 2, that gives us 21. We get the idea. We can definitely relate it to the previous, right? In this case, we'd have to relate it to the previous 2, but there is no what I'll call rule for it. We can't write a rule, but you can definitely, obviously, you have to relate it to the last 2. Okay. All right, so that's just some sequences. That's what sequences are. It's a list of numbers written from a pattern. Sometimes a pattern we can create a rule, sometimes we can't, but there's still a pattern. Okay, but it's just a list of numbers. Notice that there's commas in between. It's a list of numbers. Okay, let's get rid of that. Where else do we want to go here? Okay, so guess what, guys? We started calculus with limits. We're ending calculus with limits, okay? So the limit as n approaches infinity of a sub n of our rule equals the limit, right? Equals L, which is the limit, okay? This basically is saying what number is the sequence approaching, right? That's a fancy way. The limit is what number is something approaching, right? What number is this pattern approaching, okay? If the limit exists, we say it converges. If the limit doesn't exist, we say it diverges. Okay, we're going to see this throughout the whole chapter. If the limit exists, converges. If the limit doesn't exist, it diverges. Okay, I don't know how good, let me see, 433. This is one way visually, like if we, I don't know if this is going to show up or not, but instead of like writing the list out, you can actually plot those values, and you can kind of see how this one is approaching this limit, okay? And if we plotted the points and it just kind of went up to nowhere, then we would say it diverges. This one's kind of interesting. It goes back and forth, but notice that it is slowly approaching a value. So that happens sometimes too. So that's just a visual. You could literally plot the points if you wanted to see what's going on. Okay, so we did all that. Where are we at? Okay, let's do laws of limits. So some of this you might have to pause if you want to write this stuff down, but I'm trying to go a little bit quicker, though you know me, I'm not good at that, but we're going to try our best. All right, so this is laws of limits, which is going to look a little intimidating, and I think we've covered this before. Basically, it says, which is really nice about limits, you can break it up however you like. So if you're adding stuff, you can take the limit of each thing separately, okay? If you're multiplying, you can take the limit of each thing separately, okay? If you're dividing, now we're going to do some other things with division, but it is okay if at some point you need to do it separately, okay? What else do we have? This one, if you're taking the absolute value and it equals 0, then you can actually say that the limit not of the absolute value is equal to 0. Okay, that's kind of a special case one. Well, if we use it, we'll come back to it specifically and talk about it. And these last three, and we could even go on. It just says, hey, if you're doing something like sine, taking the natural log, taking the square root, even an exponent in general, right? Because a square root is an exponent. It's okay to take the limit of just the pattern and then do the sine. Or take the limit of just the pattern and then do the natural log. Same thing here. Do the pattern, do the limit on just the pattern and then take the exponent. Take the exponent, or in this case it is a square root, okay? So all these laws are just saying you can definitely split everything up. Everything can be independent. And this plus, actually, right, this could also be minus, right? We could also do subtraction. Same thing. All right, so don't let this intimidate you. It just means you can split it up however you like. Okay, let me slide it back one more time in case you want to write some more of those down. Okay, so if you want to pause, that's okay. All right, now, guess what we get to use? Of course, if we're doing limits, we're going to talk about L'Hopital's rule, okay, which, do we remember what that is? So let's talk about that. if the limit, and you're dividing, you have to be dividing. So remember I said this division rule we might not use quite as much because we've got lovely La Hospitale's rule. Okay, so if we're dividing, now it has to equal in 0 over 0 or infinity over infinity. The infinities can be negative, that's fine too. Okay, usually it's this guy for us. Okay, that's why I kind of jumped right to it. But 0 over 0 is okay, or infinity over infinity. Remember, if it doesn't equal these, though, you can't use his rule. So just be aware of that. Maybe if that doesn't apply, then maybe we would go to this more, okay? But as long as it equals 0 over 0 or infinity over infinity, then what did his rule say? We can actually do the limit on the derivative of the numerator and the derivative of the denominator. We still have to take the limit, but we do it on the derivative of the top and bottom. Okay, remember his only works if it starts out as 0 over 0 or infinity over infinity. Okay, that's that guy. And I'll pause for 1 second in case you want to pause it and then write that down. Okay, and we'll come back to that because we're going to use it a lot, so don't panic. Okay, let's talk about this. If this is kind of our go-to for sequences, this is one sequence that we know very routinely, and this is going to come up a lot in this chapter, like things that we kind of have to like try to get it to form to. So r to the n is big. R to the n, if you see r to the n, you know very quickly if it converges or diverges, okay? And r is just a number. So you're going to see things like 5 to the n, you're going to see things like 0.3 to the n, you're going to see things like 1/2 to the n, okay? And that's great. As soon as you see something like that, you're like, boom, I know if it converges or diverges. If r, the base, is if it's greater than -1 or less than or equal to 1. Okay, so if it falls between -1 or 1, it converges. If it's anything else, it diverges. Okay. And not only that, but then what is the actual limit? Because if it converges, we have to come up with the limit. If it's between that -1 and 1, the limit's always 0, always. And then the only other option is if it happens to actually equal 1, then the limit is 1. Okay. Because think about it, if I've got 1 to the 10th, 1 to the 11th, 1 to the 15th, it's still going to equal 1. Okay, and this, remember, this number has to be, it has to basically be right a fraction or a decimal, right? It has to be between -1 and 1. Then it's always going to have the limit of 0. Okay, so write that guy down. Okay, I think we're ready to go to examples. So let's see, I think we covered everything. Okay, so let's hit some examples. So we're always going to have notes because we're always going to have these like kind of like rules that we know the answer to right away. Okay. All right, so let's see how we're going to put that into play. All right, so the directions, we're just going to go at it. Directions are determine whether the sequence converges or diverges. If it converges, find the limit. Okay. All right, so let's take a look. Some of these we're just going to do by inspection, and then some of them we're actually going to look at the rules. Okay, so our first example is 1, 1/2, 1/3, 1/4, 1/5, 1/6, ... What is happening here? We could maybe even write a rule, but let's just talk about it. The bottom is getting bigger. The bottom is getting bigger. Eventually, we're going to do 1 over 1,000. Eventually, we're going to do 1 over 1,000,000. Because remember, these 3 small dots means it's going on forever. Okay? So what happens when the bottom gets really big? The overall value is headed towards 0. So this converges. And what does it converge to? 0. Okay? When the bottom gets really, really big, the limit, or what is it approaching? It's approaching 0. Okay. All right, how about this one? I think we even wrote this earlier. 2, 4, 6, 8, 10, dot, dot, dot. Okay, it's just getting bigger, right? 10 and 12, it's just getting bigger and bigger and bigger, so that diverges. Okay. How about something like this? 0, 7, 0, 7, 0, 7. It has a pattern, okay? Maybe we could write something out for this, I don't know, but does it diverge? It only fluctuates between two numbers, but the question is, to say it converges, it has to be approaching one number. So if it is not approaching one number, then it diverges. Okay. All right. How about let's do this. A sub n equals, so now this is more common as opposed to just visually doing it. I'm going to actually give you the rule. 4 plus 0.7 to the n. Okay. Now, if I want to see the sequence, okay, we're really not going to do that because it just kind of takes time. But if you want to see the sequence out, if you want to visually see the sequence as opposed to seeing its rule, to see the sequence, you just literally plug in, right? If I want a sub 1, I'm going to plug in a 1 right there. Okay, and then do the arithmetic. So it's going to be 4.7. Okay. A sub 2, I plug a 2 in there. I plug a 2 in there, I should get 4.449. A sub 3, I plug a 3 in there. Okay, and so I should get 4.343. Okay, dot, dot, dot. So if you want to actually see the sequence, you can. You just start plugging in a 1, write the answer down. Plug in a 2, do the whole thing, write the answer down. Okay, but we're just going to take it from the rule. Okay, so to do that, we're going to do the limit as n approaches infinity, right? Because it's getting bigger and we want it to go all the way to infinity, of 4 plus 0.7 to the n. Okay, I don't know why I put parentheses, but that's okay. Okay, so we're going to split this up. Remember, the law of limits says I can split this up however I want. So I'm going to do the limit as n approaches infinity of 4 plus the limit as n approaches infinity of 0.7 to the n. Okay. This one is 4. The limit is 4. As long as it's just a constant, that's my answer. Okay. Plus, now, some of you are looking at this going, what am I going to do with this? Guess what this is, guys? This is r to the n. This is r to the n. My r is equal to 0.7. Okay. If r falls between -1, it can be equal to 1, but in general, if it falls between, it cannot equal -1. Just be aware of that. If it falls between -1 and 1, let's see if I can find it. Okay, here it is. If it falls between -1 and 1, it converges, and the limit is 0. Okay. That's what we were writing earlier. So if because this is 0.7, it falls between -1 and 1, and so therefore I automatically know that this limit is 0. Okay. But I'm doing this whole thing, so yes, it converges, and it converges to 4. Yes, it converges, and it converges. Oh, I just made it on there. Whoa. It converges, and it converges to 4. So this is that r to the n. That's going to be huge. Okay. All right. Now, let's take a look at this guy. Okay, so here's our next example. Okay. So our pattern is, make sure you guys can see, a sub n equals 2 plus 7n squared over n plus 6n squared. Okay, Don't move. I know. If I move, I think as long as I keep my hand here, I hate how it like zooms in and out. Okay. All right. So this guy, let me put the equal sign there. Make sure you guys can see. Okay. There's two ways to do this one. Okay. Either way, when we have the rule, now remember, if you want to see what the sequence actually looks like, you would just plug in a 1, work it out. Plug in a 2, work it out. Plug in a 3, work it out. I think in a couple examples I do it again just to remind you. But that's only to see the sequence. Once we have the rule, we want to take the limit as n approaches infinity of 2 plus 7 times n squared over n plus 6n squared. Okay. All right, there's two ways to do this. One way is to, method number 1 is divide each term by n to the highest exponent in the denominator. In the denominator. Okay. All right. So we're going to divide each term, every single term, numerator and denominator, but we're going to divide it by n to the highest power in the denominator. Okay. So that means what's my highest power? I've got an n to the first and I got an n squared. So I'm going to divide I don't even care about the top. I only look at the bottom. I only look at the denominator, n squared. So I'm going to do the limit as n approaches infinity of 2 divided by n squared plus 7n squared divided by n squared, n over n squared plus 6n squared over n squared. And the whole reason is because of this guy right here. The highest exponent, I guess we could just say instead of on n, but the highest exponent in the denominator. Okay, so let's clean this up. The limit as n approaches infinity, this is going to stay 2 over n squared, plus these guys cancel, and so I just get 7. Here only one n cancels, so I have 1 over n, and then here these guys cancel, so I have 6. Okay, and then you just plug infinity in. What happens to a fraction? We've talked about this before. As the bottom gets bigger, the limit here is approaching 0. Okay, as the bottom gets bigger, 2 over a million, 2 over a billion, it's approaching. Remember, the limit is just what it's approaching. It's approaching 0. Okay, and this guy stays 7 because it's a constant. Same thing here. As it gets bigger, this guy's headed to 0, and then this is 6. So it is 7, 6. It converges, and the limit is 7, 6. Okay. All right. Now, the other way is L'Hopital's rule. L'Hopital's rule. Make sure you guys can see. Good enough. Okay. All right. So what is his rule? His rule is, so if I plug in an infinity, this is just getting bigger and bigger and bigger. If I plug in, if I plug in bigger numbers here, if I plug in, this guy's headed to infinity. So remember, I really do have to check it is infinity over infinity. Okay. So his rule says I can still do the limit as n approaches infinity, but I take the derivative of the top, I take the derivative of the bottom. Okay, so this guy, this is what? So this guy goes to 0. This then is 14n, right? This goes to 1. And then this goes to 12n. Okay, take the derivative of the top, take the derivative of the bottom. But I still plug this in, and I still get infinity over infinity. That's the only problem with Hospital's rule. More than likely, you're going to have to do it more than one time. Okay, but it goes pretty quick. You guys can do derivatives really quick. So if I get infinity over infinity, then I just have to do it again. The limit as n approaches infinity. Now the derivative, remember you're taking the derivative. Derivative of 14n is 14. The derivative of 1 is 0, right? It goes away. And the derivative of 12n is 12. Okay, so now my limit is 14 over 12. But what can happen there, guys? That can reduce, right, to, what do you know, 7, 6. So it converges. Okay. So either way is okay. You can kind of pick, obviously don't do both. Maybe in the notes we'll do a few more times both, but that is up to you. You can do either method, okay? And sometimes you'll do one and sometimes you'll do the other. We'll talk about it a few times here. Let's do this next example, okay? A sub n equals n to the third over 5n plus 2. Now remember, if you really want to see the sequence, you just plug in a 1. Write it down. Plug in a 2, write it down. So this is a sequence, but remember, this is just the rule. We're going to go right to the rules. Okay, so we want the limit as n approaches infinity of n to the third over 5n plus 2. Okay. All right, so method 1 says I'm going to divide everything by the n to the highest exponent in the denominator. I like this one because it shows that we're only going to divide everything by n to the first. That's all we got in the denominator. Okay. Remember, it's always the denominator. So the limit as n approaches infinity, we're going to do n to the third divided by n, and then we're going to do 5n divided by n, and plus 2 divided by n. Okay. And then let's simplify. What does that give us? That gives us, what, n squared over that cancels. Let's see, how are we doing? Okay, yep, that cancels, so that gives us 5. And then this gives us, that stays, right, 2 over n. Okay, so what is happening here? Let's take a look at this. This guy here, the top is getting bigger and bigger and bigger. The top is getting bigger and bigger because I'm going to take 1,000 and then I'm going to square it. I'm going to take 1,000,000 and then I'm going to square it. But on the bottom, so the top is getting bigger. What's happening on the bottom? I've got 5, and then this, the denominator, just on this fraction, the denominator, if the denominator is getting bigger, the overall fraction is headed to 0. Okay. But a really big number, 1,000,000 divided by 5, right? Because that equals, so we got a bigger number. But then I've got a trillion divided by 5, so that diverges. Okay, we cannot find the limit. All right, let's try it with L'Hopital's rule. All right, so L'Hopital's rule, the limit as n approaches infinity of, how are we doing on time? Okay. What's it going to do? N to the third over 5n plus 2. Okay, so if I plug in infinity, it's going to infinity. If I plug it in, infinity or bigger numbers, I should say, it's headed to infinity. So we can use his rule. It says then take the derivative of the top, 3n squared, and the derivative of the bottom. Well, this goes to 5, and that guy goes away. And so kind of the same thing. In fact, my denominators are the same, right? 5. But this, as I plug this in, it's just going to get bigger and bigger and bigger. How do I know not to do L'Hopital's rule again? Because I no longer have infinity over infinity, right? I would have infinity over 5, which just means that it diverges. Okay, let's try. I think, I'm trying to decide if I want to stop, because if I go too big, it's just too hard to download it. So I think I'm going to stop there, and then I'll do a part A and part B for this. so that it's easier on downloading, because downloading anything after a half hour is crazy. And the other should be about 20 minutes, so that'll be perfect. Okay, so there is going to be an A and B to 8.1.